Okay, good afternoon. Like I said yesterday, we'll be continuing with talking about conservation of energy. This is the second conservation law that we have done so far this year, the first being conservation of momentum. So let's review that for a second. Conservation of momentum meant that the momentum before an event, before something happened, usually a collision or explosion or something like that, some sort of interaction, was equal, the momentum before event was equal to the momentum after the event. And you might remember our equation for that, Pi equals Pf. That was the base equation. We expanded that out to include more terms depending on what was colliding, what was exploding. One thing you probably did forget, because I find it people always forget this, is that there's a rule for when this can happen. Conservation of momentum occurs in situations when the net force, F net, is equal to 0 newtons. And the reason for this, if the net force on the system, on the objects that are interacting and exchanging momentum, if the net force on them is 0, then what that means is, since the net force is 0, think about the definition of impulse as J equals F net times T, J being impulse, T being time, F net being net force. If F net is 0, there cannot be an impulse. And if the impulse is 0, remember impulse is just another way of saying change in momentum. If the impulse is 0, the change in momentum is also 0. And that goes for the entire system. If there's no net force on the system, there cannot be a change in the momentum of the entire system. What happens is different objects might transfer momentum back and forth, but no momentum leaves the system. Okay? That only happens if the net force is 0. If the net force is not 0, there can be an impulse in the system and therefore a change in momentum of the system. Conservation of energy is essentially the same idea, but with energy. It states that the total energy of a system before an event, and again, event just means something happens, some sort of change takes place, is equal to the total energy after the event. We symbolize this with the expression ET equals ET. It's actually on my wall at the front of my room. There's something that says ET equals ET, if you've ever noticed that. And ET just stands for total energy. Just like with momentum, there is a rule for when momentum could be conserved. There's a rule for when we use this. Because remember, our other equation is that work equals the change in energy. Okay? These are two different equations. You cannot have both at the same time. Either work equals the change in total energy, or the total energy stays the same. Obviously, they're exclusive. The total energy of a system is conserved. You can use this equation when no net work is done on a system. Another way of thinking of this is that no outside force does work. And by outside forces, we talked about this in a previous video, we mean forces that add or take away energy from a system, not necessarily forces that transfer it between different types. We are specifically talking about the applied force, tension, and the normal force here. If any of those forces does work, we cannot say that energy is conserved. However, if those forces do not do any work, remember the definition of work is force times displacement times cosine theta. If those forces do not do work, we can say that ET equals ET. The reason we don't include gravity, friction, and the spring force in here is because those forces are accounted for when we think about the different types of energy that we know about. If gravity does work, what that does is it changes the gravitational potential energy. If the spring force does work, it changes the elastic potential energy. And if friction does work, it changes internal energy, okay? And all of those can also change the kinetic energy. It's if these forces are exerted that the kinetic energy changes and work is done on the system. More energy comes into the system. So, steps for solving problems involving work and energy. I'll give it away right now. Every example that we're going to do in this set of videos, this and probably the next one, I'll probably have 2 for you today, will involve no work being done by an outside force, okay? Examples where work is done and the total energy does change can be found by looking at the previous videos when we were doing work and energy practice. So if you want to see the difference between these 2 types of problems, okay? So let's just do steps for solving problems involving work and energy. The first thing to do, I'm going to write it up here, determine if any work was done. Because remember, work means change in energy. If we're determining if work was done, we're really seeing, hey, was any energy added to or taken away from the system? Not necessarily transferred within the system, but added to or taken away from the system. We're going to have 2 different cases. If work was done, and we're going to say by the 3 forces above, applied, tension, or normal force. If work was done by those forces, if yes, then what you do is you determine what types of energy changed. And once you have that done, you use the equation work equals delta ET, like we did yesterday, where you figure out what type of energy or energies are changing. What we're going to focus on today, because we already did problems like that, is if work was not done by any of these 3 forces. It's going to sound kind of weird. You're going to draw a picture, real quick sketch. You're going to pick 2 points on that picture. You're going to label them I and F, obviously for initial and final. You will then determine the types of energy present at I and F. Set the types of energy equal. And solve for whatever you are looking for. Let's solve. Let's see how this works, okay? First few examples, I'm going to show you a lot of stuff just so that we can get all the technical stuff out of the way. Let's say that you have a 40-kilogram boy jumps off of a diving board 3 meters above the surface of a pool. How much kinetic energy does the boy have just before entering the pool, and how fast is he moving? So I'm going to draw the picture over here. We've got a boy and a diving board. Okay, he is jumping off, or more or less falling off, into the water. And we know that this is a distance of 3 meters up. We know that he has a mass of 40 kilograms, okay? Probably, what I should have done probably is figured out, hey, wait a sec, did any of these forces, applied, tension, or normal, do any work on him? If we look, applied force means someone's pushing him, there's no one pushing him. Tension means there's a rope attached to him, no ropes. And normal force means that, well, there is a normal force on him, but not while he's falling, okay? If he just, it says jumps off a diving board, let's imagine he just kind of falls, okay? Make it a little simpler. He falls off the diving board. Just kind of leans forward and right into the water, all right? If he just falls into the water, that normal force is not acting on him when he falls. He doesn't use the normal force to like jump up here. He just falls off. That normal force has not done any work on him. So, no work by outside force. And that leads to a more important kind of realization, and that is that objects in free fall conserve energy. Energy is conserved for these interactions, for these events. Now, so since we know that work was not done, we draw a picture. We have to pick 2 points and label them initial and final. It's very simple for this. we're going to say that where he starts is initial, where he ends up is final. Now, all we do is we set ET equals ET. I totally forgot to write that in. The equation is ET equals ET. That's not negative, by the way. It's a bullet point. Those are bullet points. I'm sorry. That's our equation. ET equals ET. Determine the types of energy present at I and F. Set types of energy equal and solve. So we're going to start with ET equals ET. Left hand is for the initial side. Right hand is for the final side. You can write that down if you want. Initially, on the initial side, what type of energy does he have? Is he moving yet? No. But he is above a surface. So that's gravitational potential energy. He's not moving, so he doesn't have kinetic energy. I don't see any springs in this picture, and he hasn't really started moving yet, so we can't even talk about any internal energy he's generated. So the only type of energy he has is gravitational potential. The I just stands for initial. Final, he's down here. He's just above the surface, so he's still moving, but he's lost all that gravitational potential energy. Okay? Where's that gravitational potential energy going? It's turned into kinetic energy. I'm going to put KEF, just so we know that we're talking about final, to remind ourselves. Okay? Still no springs, and most of the time we ignore air resistance, correct? So we're going to say that that's it. That's all he has. Okay? PEG equals KE, initial and final. Now we want to know how much kinetic energy he has just before he enters the pool and how fast he's moving. Look at the equation we've written down. The initial gravitational potential energy equals the final kinetic energy. We can figure out the final kinetic energy simply by figuring out how much initial gravitational potential energy he has. We know the equation for gravitational potential energy is mgh. We want the initial height equals KEF. And we can substitute in and solve. We know the boy's mass is 40 kilograms. We know g is 9.81 meters per second squared. And we know the height is 3 meters. This should be equal to the gravitational potential energy, which in this case is equal to the kinetic energy. So we find that our kinetic energy at the end is equal to the initial gravitational potential energy, which is 1,077.2 joules. There's the kinetic energy. We can also find the speed because we know that the final kinetic energy is equal to 1/2 times the mass times the final speed squared. We now know the final kinetic energy, 1,177.2 joules, equals 1/2 40 kg VF squared. That's what we're solving for. We're going to take this, we're going to divide by 1/2, divide by 40, and then take the square root. We find out that the boy should be moving 7.67 meters per second at the end. Now, some of you are going to say, wait, there's another way we could have done this, and you're absolutely right. I challenge you to think of the other way that we could have done this, maybe using something from the beginning of the year. If you figure it out, let me know. I'm going to move on to problem number 2. A 72 kilogram skateboarder at the top of a half pipe drops in and rides his skateboard to the bottom. If the top of the half pipe is 6 meters tall and there is negligible energy loss due to friction, how fast is the skateboarder moving at the bottom? For those of you who don't know what I'm talking about, this is a half pipe. We have a little skateboarder here. He is standing at the top of a 6 meter tall half pipe, and he is dropping in, meaning he's going